So in this section, we're going to see a few more convenient operational properties that will make the job of finding Laplace transforms and inverse Laplace transforms easier. And the main goal of these operational properties is actually to expand the types of differential equations that we can solve using this Laplace transform method. Both theorems we're going to see today are called translation theorems, and they're named the first and second translation theorem, conveniently enough. So let's see what they're all about. So let's say we want to take the Laplace transform of e to the at times some function. And a is just some real number. Well, using the definition of Laplace transform, that would be this particular integral here. But of course, using a basic law of exponents, we can write this as e to the negative s minus a t f of t dt. Okay, but this is just capital F of s minus a, where capital F of s is the Laplace transform of f of t. So this is exactly what we consider the first translation theorem. So this is a convenient way of evaluating Laplace transforms of functions that are multiplied by an exponential. Okay, so until the first translation theorem came along, the only way we'd have to do this particular one would be to actually appeal to the definition. That would be a very frustrating integration by parts. So according to the first translation theorem, we have this form, and we can see here that a is equal to 6. So this is equal to the Laplace transform of t to the 4, and simply replacing s with s minus 6 in our final answer. This notation means work out this thing, and when you're done, replace s with s minus 6. Note this is not an equal sign, as that would not be correct, because s is not equal to s minus 6. Okay, so we know how to find the Laplace transform of t to the n. That's n factorial over s to the n plus 1. So this is going to be 4 factorial over s to the 4 plus 1, which is 5. And we are replacing s with s minus 6. And we're actually ready to do that. So 4 factorial is 24, and we're replacing s with s minus 6. That's raised to the 5. So there it is, final answer. Okay, once again, we'll use the first translation theorem, and we can see here that a is equal to negative 2. So this is equal to the Laplace transform of simply sine of 7t, and when we're done, we will replace s with s plus 2. Okay, we know how to find the Laplace transform of sine to the kt. That's k over s squared plus k squared. So this is going to be 7 over s squared plus 49. And we now just have to replace s with s plus 2. And there we are, final answer. Okay, we can also use the first translation theorem to evaluate inverse Laplace transforms. So we are going the other way now. And we can see that we're asking for f of t, whose Laplace transform is this thing. Well, you can see that it's like we took the Laplace transform and arrived at 1 over s cubed, and then at the last second replaced s with s minus 4, right? Okay, so we'll put our attention on finding the inverse Laplace transform of 1 over s cubed. Well, we know that this is the form n factorial over s to the n plus 1 with n equal 2. So we do need a 2 factorial in the numerator. So we'll quickly balance this by writing 1 over 2 factorial here. And then now we have a 2 factorial in the numerator as desired. Okay, now if we kind of unwrap this using the first translation theorem, we would get 1 over 2 factorial and then e to the 4t multiplied by the inverse Laplace transform of simply 2 factorial over s cubed. Okay, well, 1 over 2 factorial is 1/2, e to the 4t, and then the inverse Laplace of this thing is t squared. So we basically have our final answer. Let's just write it a little bit nicer. And there we are. Okay, so if it's your life's ambition to uncover what function has this as its Laplace transform, then this is the moment you've been waiting for. So we typically approach things like this by doing partial fraction decomposition. The problem here is that this denominator does not factor. And it's for that reason that we're going to need the first translation theorem. So when the denominator doesn't factor, then we need to simply complete the square. Okay, so s squared plus 6s plus 34 is going to be s plus 6 divided by 2 is 3, and 3 squared is 9. So 34, 9 being accounted for here will leave us 25. Okay, so what we're after is the inverse Laplace transform of 2s plus 5 over s squared plus 6s plus 34. And we now know that that's equal to the inverse Laplace transform of 2s plus 5 over s plus 3 squared plus 25. Okay, great. We just need to deal with that numerator. So, of course, one thing we should do is split this into 2 separate terms. So using, the linear property of inverse Laplace transform, we can say this is the inverse Laplace of that thing plus the inverse Laplace of this thing. That's a 5, not an s. Okay, let's see what we're working with. So obviously, because of the fact that these are s plus 3's that are being squared, we know we're going to need the first translation theorem. Okay, but we're not quite ready to actually do that and jump to our final answer, because the forms aren't exactly what we want. So over here, we can see because s is in the numerator, this guy is going to turn into some sort of a cosine of kt, right? And in fact, we can see that k is going to equal 5. The problem is that we can't just factor the 2 out and then go and do the inverse Laplace transform, because the translation, that s being replaced by s plus 3, has to occur for every single s. So in fact, we really need an s plus 3 in the numerator. Okay, so yeah, let's just add 3 and subtract 3. But remember, we're multiplying by 2 here, so we have to be very careful with the way we do this. So let's see here. We want this to be 2 times s plus 3. But to keep things balanced, we just added 6 to our numerator, so we need to subtract 6. And let's not jump the gun on this one yet, because actually we have what we want right here, and then the minus 6 can join over with the other one. So what we're going to get is 2 times s plus 3 over this. And then technically we would have minus this, although I'm going to erase this in a second, and then plus that one. So actually, let's just combine those right now, and we're going to get negative 6 plus 5 is negative 1. So why don't we just write minus the inverse Laplace transform of 1 over s plus 3 squared plus 25. And over here, we can pull the 2 out. So this term is ready to finally be converted over into a function of t. All right, and we will need that first translation theorem with a equaling -3. This one over here is almost ready, but we do need a k in the numerator because this is going to turn into sine of kt, where k is equal to 5. So we have to balance that by dividing by 5. Okay, so we're ready to actually do our conversions. And note that here a is equal to -3, and here a is also equal to -3. So we're really going to get 2 times e to the -3t. And now by including this e to the -3t factor, we've kind of solved the problem of this being shifted by 3 units over, so we can just take the regular old inverse Laplace transform of this, treating this and this as simply s. So we would now get cosine of 5t and minus 1/5. Again, because of the shifting, we're going to have e to the -3t. And now we can just say, well, the rest of this is going to be sine of 5t. And there we are. There's our final answer. Okay, so let's use our new awesome skills to solve this differential equation. So, of course, we're going to start by taking the Laplace of each term in the equation. So the Laplace transform of y double prime, we know that that's s squared times capital Y of s minus s times y of 0 minus y prime of 0. And the Laplace transform of y prime is s capital Y of s minus y of 0. And the Laplace transform of y, of course, is just capital Y of s. And this is equal to the Laplace transform of t cubed e to the 2t. And thank goodness we know the first translation theorem, so we don't have to go in and do this big ugly integral. We know this is, of course, the Laplace transform of t cubed with s replaced by s minus 2. So that's going to be 3 factorial divided by s to the 4 with s replaced by s minus 2. So we get 3 factorial, which is 6 over s minus 2 to the 4th. Meanwhile, this big ugly thing isn't so bad because of all the y0 equals 0, y prime equals 0 parts that were given. So what do we have? Well, we have s squared minus 4s plus 4, and that's all the coefficient of capital Y of s. And all the other terms were zeroed out. Okay, so of course we're just going to solve for capital Y of s and then take the inverse Laplace of whatever we have, and that'll be our final answer. So this guy factors into s minus 2 quantity squared. So if we divide both sides by that, we're going to get capital Y of s is 6 over s minus 2 to the 6th power. Okay, very good. So therefore, y is the inverse Laplace of that thing. Okay, well, we know that there's a translation that occurred here. We can see that a is equal to 2. So we can write this as e to the at, which is e to the 2t, times the inverse Laplace of 6 over s to the 6. Okay, very nice, because we know that this is of the form n factorial over s to the n plus 1, with n equal to 5. So let's do a couple of things here. Let's bring the 6 out. And let's also multiply and divide by 1 over 5 factorial. And this entire inverse Laplace simply becomes t to the 5th power. So what we get is e to the 2t times 6 over 120 times t to the 5. Okay, well this reduces because 6 goes into 120 20 times. So let's just write this as t to the 5 e to the 2t over 20. And that is the unique function satisfying this differential equation with these initial values. In engineering, one frequently encounters functions that are either off or on, or that are off for a while and then after a certain point they become on. So we can represent this idea using a function called the unit step function, which is basically just identically set to 0, so it always outputs 0, except at a predefined moment, it just switches to 1, and then every number after that outputs 1. So let's quickly define this thing. So we'll assume that little a is a positive number, and that's going to be where the function switches from off to on. So the unit step function, which is denoted with this fancy cursive U, and I'm not going to write that anymore, I'm just going to use a capital U from now on, that's too hard, is defined as follows. So we say u of t minus a is the piecewise function outputting 0 if t is less than a, or 1 if t is greater than or equal to a. And we only need to define the unit step function for t greater than or equal to 0, but you could easily extend this to include all the negatives where the unit step function would just output 0 for any negative value. This is also called the Heaviside function. So the graph of it is pretty straightforward. Looks like this. So let's suppose we have a right here. Then from 0 to a, the unit step function outputs 0. And then for a and beyond, the unit step function outputs 1. So it's a very interesting function. The unit step function does provide a convenient way of rewriting piecewise functions using a single formula. So for instance, if we have the piecewise function f of t is equal to some formula g of t for t less than a, and some other formula h of t for t greater than a, then we could write f of t in the following way. We could say that it's g of t minus g of t times the unit step function plus h of t times the unit step function. So remember, the unit step function either outputs 0 or 1. So if t is less than a, then the unit step function outputs 0. And that means both of these terms disappear, and f of t is represented by, of course, just this g of t, which survives. On the other hand, if t is greater than or equal to a, then the unit step function outputs 1, in which case all three of these terms exist. But g of t cancels with the negative g of t here, and we're just left with h of t times 1, which is h of t. So the function's expressed by h of t in that case. Okay, so here we have a piecewise function, and we want to express it in terms of the unit step function. So yeah, very good. We know that f of t will be sine of t minus sine of t times the unit step function, t minus, in this case, 2 pi, because that's the threshold where the function turns on. In this case, the function turns off, because it looks like it's interesting up until 2 pi, and then after 2 pi, the function's just 0. Of course, we would add at this point 0, or whatever that is, times the unit step function t minus 2 pi. But that term is just going to disappear. Okay, and let's just graph what this looks like. So between 0 and 2 pi, we have the regular old sine curve. Now, at 2 pi, the function's not defined by the sine curve, but defined by the second definition here, which is the line y equals 0. So while for a moment we have a hole here, it's actually going to be filled in because it just so happens that that point happens to be at 0. So there's our function right there. All right, of course, this is a section on Laplace transforms, so let's see how the unit step function figures into the conversation. And we're going to see that what the unit step function brings in is we're going to uncover a second translation theorem, which will be a result in terms of the unit step function. So without the unit step function, we would not be able to have this result. So let's consider the following question. So suppose we wanted the Laplace transform of a function translated by the threshold of the unit step function and then multiplied by the unit step function. So, okay, let's just appeal directly to the definition of Laplace transform here. So that's 0 to infinity, e to the negative st times those things. Okay, but the unit step function is of course very, very predictable. So the unit step function evaluates to 0 when t is between 0 and a. And it evaluates to 1 when t is greater than or equal to a. Which means if we were to write this as the integral from 0 to a of the stuff plus a to infinity of the stuff, which we're of course allowed to do, then this would evaluate here to 0 because the t values over that interval are of course less than a, which means the unit step function would be 0. And over on this side, the t values are greater than or equal to a, which means the unit step function would just equal 1, and we would simply get the expression, but like without the unit step function. So we can just assume that we've done that and write from a to infinity of e to the negative st f of t minus a dt. Okay, so to evaluate this integral, we will do quick u substitution. So updating our bounds, when t is equal to a, u will equal 0, and then if we of course shift infinity a units, we'll still get infinity. And now we have e to the negative s times t, which is u plus a, times f of u du. Okay, so the variable of integration here is of course u. Now s and a are both constants relative to the integral, which means we can actually factor out e raised to the negative as. So we'll write e to the negative as, and then times the integral from 0 to infinity of e to the negative su f of u du. Okay, but this here is just the Laplace transform of f of t. So what we have is e to the negative as times the Laplace transform of f of t. And this is the second translation theorem. Okay, so let's use the second translation theorem to work out a few Laplace transforms as well as inverse Laplace transforms, and we will also see how this figures into our quest of solving differential equations. All right, so let's find the Laplace transform first of just the unit step function on its own. So indeed, the Laplace transform of the unit step function is equal to the Laplace transform of 1 times the unit step function. And we're writing it this way so that we can use the second translation theorem. And here we're just going to claim that 1 is our f. So by the second translation theorem, we can see that this is e to the negative as times the Laplace transform of f of t. Well, that would just be the Laplace transform of 1, which we know is 1 over s. So this is equal to e to the negative as divided by s. Okay, let's find the Laplace transform of this thing here. So what's our plan here? It's of course to use the second translation theorem. That's automatically what you should be thinking when you see the unit step function. And in order to use it, we need to make this part on the left here have the same offset as the unit step function. So we need this to all be in terms of t minus 3. Well, we're almost there. Why don't we write this as e to the negative t minus 3. And now you can see that according to the second translation theorem, this is going to be e to the negative 3s, because here we can see that our a is equal to 3. And it's multiplied by the Laplace transform of f of t. So basically now what we're doing is we're taking kind of the parent function here and throwing away the offset. So this is just going to be e to the negative t. Okay, well we know how to take the Laplace transform of e to the negative t. That's going to be 1 over s plus 1. So our final answer here will be e to the negative 3s over s plus 1. All right, here we need the Laplace transform of cosine of t times the unit step function offset by pi over 2. So yeah, what we need to do is write cosine of t in some form where we have it as stuff of t minus pi over 2. Okay, well we know that cosine of an angle is sine of pi over 2 minus that angle. So this is the cofunction identity in play here. And that's getting us a lot closer to where we need to be. But it's not quite perfect because again we're off by a negative within the sine function. But that's okay because we can just negate that and we have negative sine of now t minus pi over 2. This is taking advantage of the fact that sine is an odd function. All right, awesome. The offset matches on both sides here. So that means that we can now use the second translation theorem. And we have that this is equal to e to the negative pi over 2s multiplied by the Laplace transform of this function here without the offset. So it'll be multiplied by the Laplace transform of negative sine of simply just t. Okay, well we can pull that negative out. So we have negative e to the negative pi over 2s. And the Laplace transform of sine of t, this is sine of kt with k equaling 1, would be k, which is 1, over s squared plus k squared, which is 1. So we get negative e to the negative pi over 2s over s squared plus 1. Okay, here we seek the Laplace transform of t times the unit step function offset by 5. So what we want here is some sort of t minus 5 on this side. Okay, well we can create that. Indeed, this guy is equal to, so yeah, let's just kind of manufacture it here. We want t minus 5. But we need to keep it balanced, so let's add 5. So what do we have here? Well, it might not quite be obvious what the situation is, but we basically have f of t being t plus 5, and this is f of t minus 5. So we have the form f of t minus 5, which is what we wanted, with the function little f here being the function t plus 5. Okay, so this is f composed with t minus 5. And that's great because that offset matches the offset of the unit step function. So we can use the second translation theorem, which means that this is equal to e to the negative a, and here a is 5, so e to the negative 5s multiplied by the Laplace transform of what would be our f of t, so that's t plus 5. Okay, that's awesome, because we know how to take the Laplace transform of that. So this is e to the negative 5s multiplied by the Laplace transform of t, which is 1 over s squared, and the Laplace transform of 5, which is 5 over s. Okay, so there we are, final answer. Okay, so of course the unit step function is going to provide us with a very convenient way of finding Laplace transforms of piecewise functions. So we've actually encountered this particular example before, a couple sections ago, and what we had to do, of course, was at the time work it out using only the definition of the Laplace transform. And we had to split it, and this one part from 0 to 3, we had no choice but just to do the integration by parts. It was pretty obnoxious, and we got a final answer. So let's see if we get the same final answer, as of course we should, doing this using the second translation theorem with the unit step function. So our first job should be to write in terms of the unit step function. So we know that f of t will be this guy minus this guy times the unit step function, and the relevant unit step function here is the offset by 3, so unit step t minus 3. And then we're going to add in the t plus 1 times the unit step function, again, t minus 3. All right, so all we have to do is Laplace this lovely thing. Okay, so the Laplace transform of f of t is equal to, using linearity of course, the Laplace transform of 2 minus 2 times the Laplace transform of the unit step function plus the Laplace transform of t plus 1 times the unit step function t minus 3. Now, that part's going to take a little more analysis, but the first two terms are pretty straightforward. So the Laplace transform of 2 is, of course, 2 over s. And the Laplace transform of the unit step function, we already worked that out in an earlier example. We can see that that's going to be e to the negative 3s divided by s. Okay, so we just have to figure out what this thing is. So we have to write this as a function that's offset by 3. So in other words, we need like a t minus 3. Okay, well, let's just create it. So t minus 3, but obviously we have to add 3 back in, so we'll go plus 4. And that's the same thing as t plus 1, but it's now written in the form of t minus 3 plus 4. So we can think of this as like our f of t is t plus 4. And t was replaced by t minus 3. All right, so let's use the second translation theorem. So this is going to be e to the negative 3s times the Laplace transform of what our f of t is here, so that'll be t plus 4. Okay, so we have inverse Laplace transform of t, which we know to be 1 over s squared, and inverse Laplace transform of 4, which is 4 over s. Okay, so this guy and this guy are like terms, so we can add them, and what we're going to get is 2 over s plus 2e to the negative 3s over s, and plus e to the negative 3s over s squared. And indeed, that was the same answer that we got earlier when we did this a super long way. So we win. Okay, the second translation theorem is also very helpful for finding inverse Laplace transforms, specifically when the function of s that you're trying to apply the inverse Laplace transform to has a factor of e to the negative something times s. So yeah, let's see how this works. So if we use the second translation theorem directly, we know that we're going to get the following form out of this. We're going to get little f of t minus 6, and that's because here we can see that a is equal to 6, multiplied by the unit step function, t minus 6. So really the question is, what is this f of t? Well, we know that capital F of s is s over s squared plus 4. Why do we know this? Because imagine that we were trying to take the Laplace transform of this thing. We know that it would simply be e to the negative 6s multiplied by the Laplace transform of simply this thing without the negative 6, so just little f of t. So we can write this as the inverse Laplace transform of s over s squared plus 4 with t being replaced by t minus 6. And then this is all multiplied by the unit step function t minus 6. All right, well, we know this here computes to cosine of 2t. And we will replace t with t minus 6. And again, this is all multiplied by the unit step function of t minus 6. So what we get is cosine of 2 times the quantity t minus 6. You can write it as cosine of 2t minus 12 times the unit step function t minus 6. And there we are. Okay, so we're finding the inverse Laplace transform of an expression involving e to the negative stuff. So that means that we're going to probably need the second translation theorem, and our answer will be in terms of the unit step function offset by t minus 3. So this thing here is going to equal the inverse Laplace transform of simply 1 over s squared times s plus 1, and with t replaced by t minus 3. And this is multiplied by the unit step function of t minus 3. So yeah, our job is just to find the inverse Laplace transform of this thing. And when we're done, replace t with t minus 3, and then we're really done. So I will omit the details of the partial fraction decomposition to save us some time, but it comes out to this. So this is equal to the inverse Laplace transform of all of that stuff. And we can, of course, take the inverse Laplace transform of each little piece. So 1 over s squared, that inverts to simply t. And 1 over s inverts to 1. And 1 over s plus 1 inverts to e to the negative t. So remember, we now have to replace t with t minus 3 in that answer. So we're going to get t minus 3 minus 1, which is t minus 4, and then e to the negative of that thing. Why don't we write that as 3 minus t? Okay, so there's our final answer. All right, let's bring it all together and solve this differential equation. And it's certainly non-homogeneous because the right-hand side is actually a piecewise function. This is our very first time encountering that. So we know we're going to take the Laplace transform of all three of these components here, but we also know that taking the Laplace transform of a piecewise function is kind of a task in and of itself. So let's just start with that, and we'll do that as side work here. Okay, so the Laplace transform of that right-hand side, f of t, is the Laplace transform of f of t written in terms of the unit step function. So that would be 1 minus 1 times the unit step function. And here the offset will be 1 because that's where the behavior changes. And then plus 0 times the unit step function. All right, so let's clean this up on the inside here. We have 1 minus the unit step function. Okay, not too bad. We can take advantage of linearity property as always. And we actually know very quickly how to do each of those parts. Laplace transform of 1 is 1 over s, and the Laplace transform of the unit step function is e to the negative, in this case, 1s, so e to the negative s, all over s. So this is the Laplace transform of the right-hand side of our differential equation. So now let's just take the Laplace transform of each component of the diff EQ. So here we have the Laplace transform of y double prime. Well, we've encountered that many times. And then plus 4 times the Laplace transform of y, which is just capital Y of s. And that's equal to the right-hand side Laplace transform that we found earlier. Okay, so y of 0 is 0, and y prime of 0 is negative 1. So what are we dealing with here? Well, we can factor s squared plus 4 out of the capital Y of s, and we have a plus 1 is equal to all of these guys. Okay, so solving for capital Y of s, we've subtracted 1 over to the other side, and we also have to divide everything by s squared plus 4. So we're going to get 1 over s squared plus 4 minus e to the negative s over s squared plus 4, and then minus 1 over s squared plus 4. Okay, so we know we're going to need to inverse Laplace all of this stuff. So that's going to involve doing a partial fraction decomposition on this term here, which actually will give the same decomposition as this one, which happens to have simply an extra e to the negative s factor. So let's quickly do a partial fraction decomposition. And again, we're going to omit the details here. So this comes out to 1/4 over s plus negative s over 4, that's an s, over s squared plus 4. Okay, so our capital Y of s is equal to this term, which unwraps to the following pieces, and this term, which unwraps to the same pieces but with an e to the negative s factor thrown in. All right. So there are no like terms among these 5 big terms, so we just need to inverse Laplace each one in turn. Then our y is going to be 1/4 times the inverse Laplace of 1 over s. That one's deliciously easy. And minus 1/4 times the inverse Laplace of s over s squared plus 4. That one's also pretty easy. And now things are starting to get interesting because we've got the e to the negative s, right? So then we have minus 1/4 times the inverse Laplace transform of e to the negative s over s. And we have plus 1/4 inverse Laplace of e to the negative s times s over s squared plus 4. And finally, the inverse Laplace of 1 over s squared plus 4. Okay, so most of these we're going to get right away, and then the couple that have the exponential factor, we're going to need to use the second translation theorem, but that's not too bad. So let's knock out the easy ones right now. Inverse Laplace of 1 over s is, of course, just 1, so we have 1/4. minus 1/4 times the inverse Laplace of this thing is going to be cosine of 2t. We'll leave that one, minus this one, which isn't quite ready because we need to do the multiply by 1/2 in order to create a 2 in this numerator. So let's just pretend like we did that, and we're going to get negative 1/2 sine of 2t. All right, and now we finally need to deal with these terms that have the exponentials. So they're not too bad because we know like this first one's going to be negative 1/4. And then we can see that the a value is 1 on these. So this is just going to be the inverse Laplace of 1 over s, where t at the end is replaced by t minus a, so t minus 1 in this case, multiplied by the unit step function at t minus 1. And the other one, same kind of thing, right? So we're going to have plus 1/4 inverse Laplace of s over s squared plus 4, with t replaced by t minus 1 when we're finished. And that's also multiplied by the unit step function at t minus 1. Okay, so what do we have here? So the inverse Laplace of 1 over s is just 1. So now we would replace t with t minus 1 in that, except there's no t in there, so it's fine. In fact, let's just erase that one. And we have our unit step function at t minus 1. And what about this one here? Well, we've got the 1/4, and then this part here becomes cosine of 2t, but t is replaced by t minus 1. All right, so this is the particular solution to that initial value problem.